to talk about the real-time demand forecasting for new and shared mobility, which is based on our work in Work Package 2.1. And the focus of today's session would be on the potentials and challenges. By this, I mean for living labs, how can we incorporate this real-time demand forecasting element to facilitate new applications and solving existing challenges in what we are already practicing right now. So disclaimer, I'm not an expert in terms of like implementation and city planning, but my colleagues and supervisors from TU Delft, they have many years of experience in multiple European research projects. So I use their help to complete the expert session. So this is a joint work from everybody. And for those who are expecting it to be like a mathematical or machine learning lecture today, I might fail to cover that element today. But if you still want to know more about the methodology and models behind the forecasting element, feel free to contact me and I will send you more learning materials afterward. So let's get started. First of all, I would like to recap the challenge of the first and last mile. So in the Netherlands, we are a very small country, but we are really blessed with the well-connected NS train network across the country. So what happened in my life, in my friend's life, is especially in the south and north of Holland area, closer to the west part of the country, it's really often the case that people will live in one city while commuting to work in another city during the week. But thanks to the city level connected train service, people can just take a train and go to another city really conveniently by train as well. And the frequency of train is also amazing. But this type of lifestyle also brings in another challenge. So we are not all live nearby the station. So the Dutch way is normally they would take a bike and bike from home to the station. And some people even have another bike in the city where they work. So they take the bike again or take public transport to their work location. Then here brings the first and last mile challenge. How can we make this trip a bit more convenient for different types of passengers? Although in the Netherlands people own multiple bikes themselves because of similar reasons, but there would be a way to improve or adapt this lifestyle a little bit. For example, by introducing share bikes and share e-scooters near the station, so people can use the share service without having to find a place to park their bike or without having to purchase another bicycle just to complete this trip. Right. And yeah, talking about new and shared mobility, we have so many possibilities in recent years, and there are different types of solutions. So this slide was given to me by Gonzalo, but that was based in past projects for the city of Utrecht in the Netherlands. In that case, we investigate about, as you can see on the screen, so many different options that we can choose to incorporate. So we have share bike, share e-scooter. These two kinds are quite popular in the Netherlands because we're a flat country and people do have a good culture of biking on the street. And the facility in the Netherlands is also great for biking. But considering there are also passengers, for example, the older people or there are people who might need to use a wheelchair, it would be more convenient for them if we can have on-demand services such as a shuttle bus or minivan that can connect them door to door from origin to destination. Besides of that, we also are promoting the use of e-bike and e-scooter. Also, there are carpooling and car sharings, and there are different types of vehicles that people can choose from. Then it comes the question, as passengers, while they're considering to connect their multimodal journey with shared vehicles, they would wonder where would be my fleets, where I can get a service. So then I don't need to walk for too far, or I don't need to wait for too long for something to become available. Well, the service providers, they will ask, okay, where are my demands? At the beginning of the day or during the service, they might observe that their vehicles have been redistributed around the city because of the pickup and drop-off requests. But they would prefer to match the demand and supply at the right timing, so then their users doesn't have to wait for too long, and they will not. Is there a question? Okay, now I will go on. So the supply and demand can be matched, and they on one hand to uphold the passenger user experience. On the other hand, they can also achieve profitability by enhancing the utility of this shared vehicle service. However, as a cliche, we all know that the urban transportation system is full of uncertainties. There are uncertainties from the public transit, such as when the bus will arrive. Is there any chance of disruption during the day that we cannot foresee? These two types of question has been widely discussed in like public transit studies for bus network, for metros, and for trains. Because of the on-demand services like taxi and Uber rides, people also start to investigate what would be the trip duration for these ride-hailing services. And I would say the common interest of different components of urban transportation system is the demand. Where is the demand? When would be the demand? And how demand is matching to the supply of the services. This is a question that's interesting for both the passenger and for the service provider. So naturally, that would be the focus of our talk today. And to predict the demand, we need a little bit more like intelligence in the method that we use. So I know generative AI, GAI, has been a big talk recently because of the rising of ChatGPT, for example, and you see implementation for video making, for large language model in answering questions. It has really gone down to our daily life. But recently, I read this article. It was a review of a talk by the AI giant Yann LeCun. So for the information, he's the author of the convolutional neural network. So you can see him as one of the most experienced scientists in the field of deep learning and AI. So that's what he says. In many ways, common sense amounts to the ability to predict what's going to happen next. This is the essence of intelligence. What he's trying to emphasize here is, although in large language model, we are able to predict what would be the next most likely word given on a piece of text. However, if we project this capability down to real life, there are so many things we still need to predict. For the transportation case, we want to predict what would happen if I rebalance the fleet to a different location. Would that lead to better utility of my service? Would that help me satisfy more customer in the future? Or would that do the opposite thing? That's what we're trying to know. But to do the investigation of what would happen for this implementation, we first need to know what would be the demand that might assist us to make such decision. Then it would be wise for us to first define what are the what are the forecasting problem we're dealing with. So in work package 2.1, we will implement a forecasting framework called spatial temporal demand forecasting. And there are two levels we need to predefine for the forecasting task. The first level is the spatial granularity. Depending on the service, for shared micro mobility service, for example, in Munich, we have different docking stations for the bikes. So this service is called dock base. If the user always have to pick up and drop off their bike at certain location. And for instance, if the bike can be parked anywhere within the service region and can be picked up anywhere where there is availability, then we will call this type of service dock free. Also, free floating services. At the case of dock-based services, such as the visualization on the left, there are many points that of demand, but this demand needs people to walk to them to get accessibility to. But if it's free floating, that means demand and this request can literally pop up anywhere in the city. So a common practice in industry is to desegregate the service map into a set of connected grids. And Uber actually introduced a system called H3, which means they can separate the city into different size of hexagonal grids. And hexagons, they have a really nice features of equal edge length. And if you connected the center of the hexagon, it would be like a triangular network that makes optimization and other computation easier to perform. And we can make prediction at per station and per grid level. And on the other hand, we can also connect the demand prediction with the origin and destination of the trip. For instance, we can predict things like if a bike is going to be picked up from a station, what is the likelihood for it to end at any of the other grids within the city. Then this pairized kind of prediction is normally called the origin destination forecasting. Having introduced the spatial level, we also need to consider the design of the temporal level. For the temporal granularity, there are two aspects to be considered. The first one is the frequency of data. Frequency is like a terminology in classic time series study. It means like how frequently we are gathering the information in the system. For example, the software, the computing center of a service can gather information of where its vehicles are every 15 minutes. Then every 15 minutes, this is the frequency of the of the data stream. And frequency can also be defined for the forecasting task as well. For instance, how precise we want to be in terms of the updates of information. If we want to receive a new prediction every hour, then 1 hour would be the frequency of forecasting. Then the other aspect is the forecast horizon. The horizon, as shown in the figure, it means how far into the future we are interested in predicting. I think in most literature, the forecast horizon is set to 1 hour. However, with this, with our project, we aim to scale up the forecasting horizon to per 15 minutes. Why we are doing that? Because if we have predictions for per 15 minutes, is better matched to the operation frequency of the new and shared mobility company as well. Imagine if we have prediction for 1 hour in the future, but most trip of bike sharing ends from like 10 minutes to 30 minutes, then it doesn't gain much from 1 hour's like prediction, because we anything could happen within the 1 hour. But by scaling up the prediction frequency to per 15 minutes, then we can match like, okay, we have more information of what will happen in the near future, so we can also perform this real-time strategy of rebalancing or dynamic pricing in like a more timely manner. So that comes into effect in matching the operation and the forecasting frequency. Right. Okay. Then having introduced the definition of forecasting task itself, in the next part of the presentation, I want to show you a couple directions that it may be interesting to apply forecasting to different shareholders of the urban mobility system. The first potential I want to introduce is the joint planning of public transport and new and shared mobility services. So in this paper of Odette, it says, okay, so there are two levels of services. The bottom level is the public transit. And public transit normally, for example, like metro or train, it follows a route and a network. So when a train started in the network, we can get information of when it will arrive to the next station, and we can estimate how many people are going to check out at those sequential stations in the future. And with this information, we can connect the check-in and check-out demand of the metro station and project it to demand responsive transit services. And the assumption of it is this type of multimodal PT plus NSM journeys can benefit the passenger to further shorten the total journey time, and also improve the utility for them to have a more enjoyable trip. So the joint planning of public transit and new and shared mobility is also the idea of it's also the idea of Work Package 1 for our collaboration with RET. And we will come to that later to explain what our implementation is. And next one is from the new and shared mobility service perspective. Like this company, most of the case, they're new, and they need to survive in the market. Therefore, it's important for them to have a relatively high utility of the fleets. I think such example, we hear stories from Munich for the SIG service, and also from Jerusalem for their ride-hailing services. It's really the bottleneck for over the years for this company to be fully use the vehicles and achieve profitability and sustain as a business itself. So if we can incorporate the demand prediction with real-time fleet operations, this company can dynamically reallocate their fleets to where the demand is demand like hotspot is. So for example, in this framework, the author first analyzed the network structure in the service network, and they predict the trend of historical travel demand. And nevertheless, they also take into consideration external factors like the dates, the weekdays, and what time is it, how's the weather, and then use this all three sources of information to generate a trip demand prediction. Then this prediction would be considered jointly with what is happening in the system. For example, how many parking spaces left and how many available vehicles the company has around the city. Then it make decision to reallocate the vehicles and rebalance the stuff. Then you achieve like a better objective in making use of available vehicles in the system. Yeah, this is a paper that Gonzalo has worked on. I think he's also in the call today. So if you have a follow-up question, then I think he will be happy to answer. So this is an example of how this shared mobility company can make use of prediction as an assistant to further optimize the operation. Then another, I think, rather successful use case of prediction for shared mobility is the demand and supply nudging via dynamic pricing. So this is like business scheme from Uber. So I think mostly in US, they have this system called surge pricing. And they explained it that surge pricing for driver is an incentive for them to willingly reallocate to where the demand is high and supply is low. And for the passenger themselves, by putting the extra price in the trip that they're willing to pay, they might also get priority of the service. So they describe it as like a win-win strategy to match the demand and supply by changing the behavior of both the driver, aka the supplier, and the passenger, the user. And amazingly, I find one of their integration in the app is to generate a heat map of the search pricing scenarios across the city. So how the heat map work is whenever a passenger put in the search pricing, it would change like the demand level that visualized in the map. So if the color is becoming hotter, that means there is a huge demand. And for the drivers, that is a huge incentive to drive towards the area, not necessarily to certain points in the city, but to drive towards where the demand is high and supply is low. And this heat map can also visualize for the potential Uber user to tell them, okay, if you, for example, if they could have take metro or other public transit to another area and connected to Uber, then they might prefer to do so because there's a high likelihood for them to pay extra for such service. So this heat map is like a nice functionality to like at the real time to incentivize the driver and to inform the riders. Yes, and the last example I want to give is what we are working on in Work Package 2.1 with RET from Rotterdam. So in like a MOS system, we have platform and we have user service provider. And the MOS system need to connect the information from these multiple parties and to facilitate the choices of passenger and the running of this public and private service provider. And on the user, the other hand, what they get information from the MOS platform is they will see what type of service are available to them, and they would put in their trip, like origin destination request, and see, okay, what would be a recommendation for them to perform a trip. So it's kind of like Google Map. You have origin and destination, and then there are multiple ways that you can realize the trip. And in Work Package 2.1, the public service provider is RET. They have tram and metro service in Rotterdam, and Siemens would be the IT, the cloud computing units that helps to connect the prediction results in real time and feed it back to the MOS service to facilitate this information bridging. And check is the share e-scooter partner we have in Rotterdam, and they would feed to us information in real time about where the fleet is, and where the fleet is also includes information about the level of charge for different vehicles, and also the status of different vehicles. For example, they're on a trip or they're idle. And as we highlighted here, real-time information can be expanded with real-time predictions. And our prediction includes pickup demand, drop-off demand, and also fleet distribution across the city. And with our end product of Work Package 2.1, what user can be benefit from extra is the availability likelihood we estimate at real time for them to check whether they're unlikely, likely, or very likely to get a idle check scooter when they arrive to one of the middle stop or when they arrive to their origin. So this extra like prediction really gives them the insight, like sets them an expectation of how likely they're gonna get the service. It's possible the case that if it's unlikely for them to get the service, they would have to choose an alternative way to achieve their travel. And if it's likely, then when they arrive, they know that they have the option to take this from public transport to shared mobility transfer, and they would be encouraged to do so. Yes, and I will just fly by these slides. So this is the method that we use behind the prediction, real-time prediction framework. And the core of the method is to use XGBoost together with time series elements that describe the underlying demand pattern. Right. So we also need to consider multiple sources of information, including the weather and also how's the public transit service is running, whether there's a disruption going on, and whether they expect service closure in the upcoming days, for example. And with the prediction made, this information will be fed in real time by Siemens API, and then passenger from the front end can put in a request. The server's gonna process it, obtain the prediction, and then feedback to the passenger with the predicted availability of new and shared mobility. Right, and we have trying to in the process of producing a paper about it. Yeah, so we have around 5 more minutes. I will talk about the challenges that you might come across in implementation. So the challenges that we learn from the work package is it's really hard to convince the operator because they're private sectors. They need to feel secure. They need to see the value for them to share such data with public transport and with the mass service in general. And also they would like to have this safety net that their information would not be accessed by in any way other competitors in the market. So it is important to convince them why this kind of functionality could be useful for them. And on the other hand, because we do have multiple sources of information coming in to the API in real time, then we need a scalable service that can handle this computation fast and accurately. But thanks to Siemens technology, we're able to do this conveniently. And then the data engineering part is to outline the formats of different data. And another challenge that might pop up is the demand forecasting might not reflect what is the real potential demand in the market. Because what we observe from the past is the demand that has been realized, but there are also demands that the operator might have missed because the supply was not there and passenger cannot take the service. Then my supervisor Shadi has a paper to discuss how to estimate this part of missing demand and in a revenue management perspective. And this kind of service can also give insight to operators to suggest them if you could have done better, how much revenue you could have gained. And the last part I want to emphasize is passenger behavior. So previously in the presentation, we have been talking about the aggregate demands of a population of passenger, like when they come to a station or depends on where they are when they initialize the request. But how individual passenger would choose is also important because we have individuals that can be described by different characteristics. And what they would choose is important in what would be the best mode choice for these different individuals. And especially if a mass app wants to provide the most suitable travel recommendation in real time for different individuals, then it's important to analyze what is the best for them. So in a past research of Gonzalo, we analyze what's the preference of passengers based on different activity and the location of the activity, and they design a menu of different options for this survey participant to choose. And there we can estimate the utility function for how what's the acceptance of using shared mobility in combination of public transit, and what is maybe the value of time and the value of pricing of different products. And with this passenger mode choice analyzed, and with the short-term demand forecasting, my colleague Iman is working on a paper that can real-time generate the trip recommendation based on these two inputs and try to realize the system-wise optimal in organizing the fleets, in optimizing utility of all. By utility, I mean like the better option of all the passenger. So a concluding message here is, yeah, real-time demand forecasting may be a useful tool for your use case, and there are multiple potentials in enhancing the performance of the new and shared mobility companies itself, in promoting multimodal travel at the city level, and to generally give more information to the passengers who are using the service and there to facilitate this lifestyle of multimodal travel. However, it's also challenging, especially in the data collection and processing parts. You might need a strong case to convince the partners, and you also need the techniques to perform this. And also, never to forget to analyze the behavior at the passenger level. And it's important to know the passenger in order to nudge the demand of them. And yeah, that's the end of the presentation. I know it's a long one. And this is the team of TU Delft. I'm missing Iman here, sorry, because I only put the work package 2.1 people here. But Iman is also in the chat if you want to ask question related to that. And thank you for listening.
Thank you so much, Rina, for this very comprehensive presentation and showing the different use cases for which the prediction tool can be used. I think also for the observer cities, I hope it was helpful and interesting and a nice input. And I'm sure that if they have any very deep questions about it, they are able to contact you afterwards, right? But if you have any questions right now, feel free to ask. But yeah, thanks again, Rina.
Thank you for listening.
And you're producing a lot of papers, right?
Those are like past research paper from the TU Delft team. And, they really covered like different aspects, and they have all kinds of creativity in facilitating multimodal travel in different city use case. So maybe not within the project, maybe in the future, it's also good to, have in mind, and maybe we can make the connection happen.
Nice. Are there any questions from the audience, from the observer cities or the living labs?
Well, actually, I have one from Tel Aviv. I have my friends here, Michal Kamun and Alma and Batel. So if you have also any questions, just pop in. I would like if Rina can a bit elaborate, because we were not involved earlier, but if you have any ideas or resolutions regarding pickup demands at peak hours. I mean, when people get off the train and at the peak hours and actually there's not enough available tools, what are the resources are you offering during this project, or were you handling that?
Yes, clear. So the question is about how can we use forecasting to solve the undersupply during peak hours. So actually, there's a paper about rebalancing. So what we observe in my current study is there in a city, normally there are different hotspot of demand during different time of the day. So rebalancing means if we can identify dynamically where the hotspot of demand is, we can proactively rebalance the vehicles from the areas that relatively have lower demands, proactively rebalance them to the hotspot area, so that we can proactively prepare for the peak hour. And that's one thing. And the other thing is it is good to estimate in a simulation how many bikes are needed to satisfy the demand. And then if the bike resources is not available to be more, then what would be alternative solution maybe on the public transit side to resolve this kind of stress? So that's why we want to promote the multimodal travel between public transit and shared mobility, because it's possible that we can redirect part of the passenger to get out a stop later or earlier, then they can use the resources at these two relatively less stressful area. Then this trip recommendation is designed to resolve the stress of mobility in the network level.
Thank you very much.
Glad to help.
Any further questions? Okay, I think it was a lot to digest, but thank you again so much, Rina, for this thoughtful presentation. And I think that a lot of people will have a look at it afterwards, and maybe if there are some questions, you are available, and thank you so much for that.
Thank you for having me.
Okay. There's one question from Priska Ertico.
Hi, Pauline. Not a question, but I would like to thank Rina for the very nice and detailed presentation. It's good to have understood more all you're doing within Work Package 2, and we will do well to disseminate this session because I think it will bring more attention to what we are doing within the Zone project and show our progress so far. I also wanted to mention to all the Living Lab partners here, please, if you have any communication that you would like us to bring forward in the next month, despite the holidays, kindly send it to us or to my colleague Anoa. Unfortunately, she's not here, but we'll be happy to hear from you. Thank you.
Thank you, Priska. Okay.